So now we're ready to start. So I'm going to give you a small intro on who is Benj. So Benj did his PhD at Oxford modeling the flocking behavior of birds before turning his attention on how digital product can learn from masses of data on human behavior. So very, very actual. He has been a senior data scientist at Cleo for the past 2 years and working on machine learning models used in the Cleo app. So please welcome Benj.
Whether it's better, there we go. Testing. So the topic of this talk is testing. Want to test in production whether it's better, whether my new model is better than the incumbent system. So I'm going to start by talking about introducing Cleo as a company, why to do A/B tests, what you need to decide before starting the test, including choosing how you'll analyze the data, how you'll make a decision. I'll go over why we use Bayesian A/B test analysis at Cleo, and how to interpret metrics within Bayesian A/B test analysis like win rate and expected loss, and some of the maths behind those metrics. So who is Cleo? Well, Cleo is all the things that it says on this slide, but most importantly, Cleo is a chatbot who engages users about their personal finances using a casual tone of voice. And Cleo is designed for people whose financial health isn't in such great shape. So maybe they have a poor credit score or a lot of credit card debt, living paycheck to paycheck, and is designed with the considerations of those users in mind, and aiming to follow them on a journey to better financial health. So things like avoiding going into their overdraft, building their credit score, developing the saving and spending habits that work for them, and becoming more financially secure. And as we do this, we're releasing more and more features in Cleo. So things like a credit builder card, a new budgeting feature, and all of these, we need to test their impact. So we're also running more and more A/B tests, and somehow in the last 6 months, it's really taken off and gone crazy with the number of tests we're running. And this is partly because we're really growing as a company. We have more squads, shipping more features, a bigger data analytics function able to support testing those features as we release them. So why do A/B tests? Well, an A/B test is also known as a split test or a randomized controlled trial. It's an experiment that you use to test the impact of a new experience on some sort of outcome metric. So say we were interested in conversion rate, and we have a new onboarding experience for the app. We're interested in more users are successfully onboarded. If we just released it at a certain point in time with that purple line, it might coincide with something going on in the world, like a stimulus check going to all of our US customers. We wouldn't know what the impact was. So we think that just looking before and after, we think, well, that could be due to the new onboarding experience. It could be something else. If we ran an A/B test of new onboarding versus old onboarding, we might find, oh, well, actually, the new onboarding has had a subtle has caused a subtle decrease in the conversion rate, and we can only do this through an A/B test. And A/B tests also help us reduce risks. So we use our A/B testing framework to do gradual rollout of new features. So we might start it with only 5% of the users on this new variant, and then gradually ramp it up to 50% Or if we had, if you have enough traffic, you could run the A/B test on only 5%, but it would take longer to reach your conclusions. So why do that? Because testing 50-50 from the start is going to enable you to learn the fastest which thing is better. Well, that's because in A/B testing, we really have two aims. We aren't just scientists trying to figure out what the difference is between two different treatments. We're also advising the business on the best course of action. So, in other words, there are two conflicting aims somehow in A/B testing. We want to measure which version is better and by how much, but we also want to have an impact by exploiting our best bets. So the measurement aim leads us to use holdouts, for example, which I'm going to talk about in this talk, and also reporting win rate. So what's the probability that our new version is better? When it comes to exploiting our best bets, that's why we use a testing framework that enables early stopping, so more people can have a promising new change to the product sooner. And it has also led us to use Bayesian multi-arm bandits, which I won't have time to go into in this talk, but when you're thinking about an explore-exploit trade-off, this, I think, is a theme that runs through A/B testing, because, as I said, we're not just trying to determine the difference between two things. We also need to advise the business on what risks to take. So what needs to be decided before starting a test? Well, we need to decide on our hypothesis, decide what it is that we're testing, and framing the hypothesis at the start really sets the test up to ensure that you can always learn something concrete, even if the test wasn't a success. Defining the metrics ahead of time is very important, so you're not picking and choosing metrics that tell a particular story after the test is run. You need to know what variance, and you need to know the exposure point. So in other words, like which users are eligible for test, what's the denominator of your success rate. So I'll illustrate these things using an A/B test that we did within Cleo. So during the budget setup, one of the things is a user has connected their bank account to Cleo, and we try to automatically detect their recurring income and say, let's tag your pay. So say we have a new income classifier that's looking at this sequence of credits coming into the user's account and trying to identify the merchant, the schedule, when they'll next get paid. And so that's affecting this part of the UI. And for our success metric here, we might just base it very simply on the next action that the user take. So did they say, yup, that's right, going to the boom, done, income added screen? Or do they say, no, sorry. So that's very like proximate user feedback. Did we give better details? So in that case, our success rate would just be the proportion of users who land on this page who say, yes, that's right. The hypothesis is that the new income classifier will give better results, and therefore more people will click, yup, that's right. And it's always good with a hypothesis to say why you think a particular change will have a particular impact. So in this case, we might say, well, we've got this gold standard offline data set for income classifier evaluation. This new model is doing better on that data set, so we've decided to go forward and start the A/B test. The variance here would just be the new income classifier versus the old income classifier, which is the control. And the exposure point is this page. So we're not saying what proportion of all users in Cleo click, yep, that's right. It's just of the users who land here. That's when the users get bucketed into the test. So this is a great way to evaluate a single test. But what if we have many tests over time, and we want to? What we found at Cleo was that when it comes to the end of the quarter, and you're thinking, okay, well, what impact has your team had on this metric, like conversion? then we're going back over the A/B tests and saying, okay, this test gave a 5% improvement, this test gave a 10% improvement, and those improvements might not match up to how the conversion rate moved over the quarter. So what happened there? Was it that one of those was a false positive? We thought it was a 5% improvement, but it was actually a change that caused a decrease in conversion? Or was it something another squad did that was maybe, in order to get a better cost per acquisition, we moved to a different advertising channel, different kinds of users were coming in, and that we'd always expected that would have a particular effect on conversion. Or maybe there was a macroeconomic factor and people were something was changing with our users' finances over time. The pandemic, great example, has affected a lot of people. So a holdout is essentially a long-running A/B test where you take out a small portion of the users and don't expose them to the new changes. And we tend to do this by squad. So a particular squad at the start of their quarter would say, okay, this 5%, we're not going to roll out the new things to them. We'll see how they fare. And each A/B test would just be on the non-holdout users. When you discover which variant you want to promote, you promote it to all of the non-holdout users, and the holdout users end up carrying on getting an older version of the product. And so if you think about exploitation, we're continuing to explore how the older version of the product would have done so that we can have a more accurate measurement, while most of the users are getting what we think are our best bets from our A/B tests. So it's also important before starting the test to choose how you're going to analyze it, how you'll make a decision of which treatment was better, right? And a first consideration here is your success metric binary or is it a continuous variable? So binary would be like conversion rate, each user is just a success or a failure. A continuous might be your revenue from each user. What I've found is that most A/B tests, binary works, and that's what I'm going to talk about in this talk. There would be different analysis methods that you need for continuous variables. Another choice is, say, a statistical framework like frequentist or Bayesian, and regardless of which one you choose, you need to pick some parameters up front that define your decision point. So for frequentist stats, you choose a threshold p-value, your significance threshold alpha. You choose a minimum effect size that your test is able to detect, and then the power, which is the chance of detecting that effect when it exists. And those three things together, you can calculate sample size, which is another thing you need to know ahead of time. For Bayesian stats, there are also parameters you should choose ahead of time. So for example, the maximum expected loss. And this talk is mostly about Bayesian stats, so I'm going to go into some detail about how to calculate that. One of the reasons we prefer Bayesian stats is we just find that something like win rate is easier to explain than a p-value. So p-value answers the question, how likely am I to see success rates at least this different if A and B are actually the same? Whereas win rate is just, what is the chance that A is better than B, which is more the kind of thing that a product manager is interested in. And the other thing about Bayesian stats is if there's a clear winner, like say the effect size seems to be much bigger than we expected, we could stop the test early and promote it to all of the non-holdout users. And the expected loss decision rule that I'm going to explain in a bit, it tells us the magnitude of the risk that we're taking when we stop the test and promote the winning variant. So I'll go into some detail now about where this win rate number comes from. And the problem that we're trying to solve with win rate is when you run a test, you won't see the same success rate for both variants. So say we were running a test and we see 62.4% for one, 68% for the other, different success rates, but is this noise or is it a signal of these treatments actually being different? So say each of these percentages was based on 1,000 users. So you had 624 wins out of 1,000 for one and 680 for the other. And as I'll show next, each of these can be used to calculate a beta distribution, and from that we can get a win rate to tell us, well, the probability with these numbers of wins and losses, the probability that the higher success variant is better is 99.6%. So in that case, we'd be likely to stop the test and say, okay, we're 99.6% sure that it's better, whereas 50-50 would be saying, well, no, it's just noise. So the beta distributions are a probability distribution between 0 and 1 with two shape parameters. And for this type of analysis, the shape parameters alpha and beta are both positive integers. Alpha is based on the number of observed successes. Beta is based on the number of observed failures, and each of these are also affected by the prior. So the more observed successes and observed failures you have, the narrower the distribution, so the more confident you are that the true success rate of this variant is close to the mean. The mean of the beta distribution would be your observed success rate. And to calculate a win rate, one way of doing this is with sampling. So from each of these distributions, sample a success rate, which one is higher, and then out of a large number of samples, the proportion where red is higher than blue would be the win rate for red. And so therefore, the more that these distributions overlap, the closer it will be to 50% win rate, and the more distinct they are, the closer to 100%. Another way of imagining this is if you plotted each of these distributions on a different axis. So one is on the x-axis, one is on the y-axis, as giving you the joint distribution. Then the win rate is the probability that falls into that top left triangle. So summing up the probability density there gives the win rate in this case. And so that therefore you can do this with integration in an analytical way rather than sampling, but both of them give the same result. Now I mentioned priors earlier. Priors, it's nothing to do with monks, it's the prior belief about the success rate. And we tend to use an uninformed uniform prior. So this is alpha equals beta equals 1. It's a uniform distribution saying we don't really know what the success rate will be ahead of time. This is a little bit unrealistic because we often do have some prior information on the success rate, but we find that we can, in most product areas, we can collect so much data so quickly that it just makes sense to base our conclusions on the observed data. Now, you might sometimes read that priors can help speed up the decision process or make faster decisions with less data. And this isn't actually true. The stronger the prior is, the more it will delay making a decision until you have enough data to overcome the prior. So priors can be a good way if you're forced to make a decision with only a small data set to make sure that decision is robust. And what the prior effectively does is it formalizes your hunch that actually I don't think conversion rate is going to be 90%. And if I saw 9 out of 10 people convert out of only 10 people, I would say, well, that's just because it's a small sample size, it's a fluke. And the prior just formalizes that by adding in my prior belief that the conversion rate would be, say, around 40% or whatever it had been previously. So how do we decide a winner? How do we decide when to stop the test and call it? Well, I think there are different considerations that you need regardless of the statistical framework. One of them is to have guardrail metrics. So by guardrail metrics, I mean secondary metrics that you're monitoring as part of the test, and if these make a sudden change for the worse, then you can stop the test and investigate what's going on, and this helps to limit the risk. So for example, if I was running an, which I have done previously, email content optimization A/B test, where we're trying to get more people to click through to an app or a website from the email, but people can also unsubscribe from the email if they find these emails really annoying. So we want to make sure that the unsubscribe rate stays low while improving the click rate. The unsubscribe rate is already low, so it might be, because it's close to zero, it would be difficult to find to evaluate as a success metric. It's not our primary thing that we think will move, but we need to monitor it, because if it goes way up, then maybe we've annoyed people. It's also useful to pick a minimum test duration based on the cycles of activity within your product. So at Cleo, there are daily cycles of the users waking up and checking the app. Obviously, there's also a weekly cycle. Many of our users get paid on a Friday. They spend more money on the weekend. We send notifications, like there's a game notification that's very popular that goes out on a Saturday. Budget notifications might go out on a Tuesday. So that means if you only ran your test on a Monday and Tuesday, it's not representative of the whole cycle of a week. And so we might decide ahead of time, well, to be safe and make sure that we're measuring how this will really perform going forward, we need to run it for a minimum of a week, unless one of those guardrail alarm bells goes off, and then we might stop it and see what's going on. It's also important that the decision rule reflects the company's appetite for risk. So the context in which a lot of our Frequentis stats were developed is things like medical research, where you don't want to give a medical intervention, you don't want to inject something into someone if it's no better than a placebo. You would rather just leave that person alone. With our digital product changes, often the change, say it's like a user interface change or a machine learning model, it's already been developed, it's already been QA'd, it's ready for production. So the cost of it is up front, and if it's no better than the control, that's not a great loss to the business. We're talking about changing a feature that the users are going to be experiencing one way or the other. So in this case, if two things are roughly equivalent, we would be fine with deploying the new one. It doesn't make a difference to us. So make sure the decision rule reflects the risk appetite, and in this case, it would say, if two things are equivalent, it was fine that you deploy the new one. Just check your holdout to see whether you overestimated the benefits that it gave. So how to decide when to stop the test? Well, with Frequentis statistics, it would be wait until you've reached the agreed sample size, so it's a fixed horizon test. With Bayesian statistics, we would run the test for the minimum cycle that we wanted to, and then check whether there's a clear winner with a high win rate and a low expected loss. If the test ran for a long time and there was no clear winner, then there might be another version that was ready to be tested, and we wanted to stop this test to make way for something else that we thought was more promising. So the cycle ends up looking like this. We would collect data, then calculate the win rate on the first period of data, apply a decision rule, such as rope or expected loss, and then if the experiment is conclusive, we would end it, or if the experiment had run on for too long, we would end it. Otherwise, we could collect more data, periodically monitor it, check our metrics, see whether it was time to end the test. And these decision rules, rope or expected loss, are what I'm going to talk about next. So expected loss means how much would we lose on average if the current winner was actually worse. And so expected loss is in the units of your success metric. So say it was like your success rate, the user's success rate of setting up bills, then an expected loss of 0.1 would mean 0.1%, would mean 10% of users. The expected loss would be that 10% of users may be not setting up bills. And that loss would be above our threshold of caring, whereas a smaller expected loss, we might say, okay, we're willing to take that risk. ROPE stands for Region of Practical Equivalence. And for those of you who saw the Product Madness A/B testing talk, that was about the ROPE decision rule and whether the most likely effect sizes in the test fall far from 0. So we mostly use expected loss at Cleo, although we're a young company, we're open to trying different things. I'll explain how expected loss works. So the graph on the left is the same one that you saw earlier for win rate. So this is the joint probability distribution from the two beta distributions for the control and the test. And that bottom left triangle is the region where the test is doing worse. So if we're calculating the expected loss of choosing the treatment called test, then we would take this probability that it's worse and multiply it by the impact of being worse. So some of this kind of blue shaded region in the bottom left, in the bottom right, is actually does cross over the line into into the region where test is doing worse, but the magnitude of this is quite small. So as the test goes on and the joint distribution gets narrower, then the situations where it's worse are less likely, and they also have less magnitude. So as an example, in this A/B test was about a bill matcher. So a model that would look at new transactions coming in and classify, do we think this is a subscription payment for one of the user's existing bills, or is it unrelated to their bills that they've set up within Cleo? And in this case, it was very clear, more than 99% win rate, very low expected loss. It shouldn't say less than 0, it should say less than 0.1, but the tabling framework that we use tends to round things down in a way that's not very Bayesian, but that's what it means. So very low expected loss. We're safe to go with this. Here's another example. So we have a product called the salary advance, and we wanted to make a copy change around explaining to users how this salary advance money would arrive in their account. And in this case, the success rates were very similar. The proportion of users taking a salary advance with the new copy or with the old copy, 15.6 or 15.5%. The win rate, therefore, is not very extreme, but the expected loss, because of this large sample size, the expected loss is also gone down to around 0.1%. So we would say, well, even though we're not really sure which of these variants is better, we still think that it's safe to go ahead with this new copy. Now, I should mention the hazards of early stopping in terms of spotting false positives. So here you might think, ooh, 95% win rate, low expected loss. It's safe to stop this test. Now, it turns out this was an AA test where we were using two bill matchers that were both the same. It's the same model behind both of them. And it's possible to simulate this kind of AA test on past data as well. So I guess, strictly speaking, the expected loss, it's correct that the expected loss is low because the two things are the same. We're not going to lose anything by choosing one or the other, but it gives us a false positive that maybe the success rate was 5% higher with one than the other. And as you can see, like quite small numbers of users involved in each one. So there are different ways that you might combat this. Could use an informed prior, or could use a different decision rule. The rope decision rule framework is more oriented towards telling you if your test should keep going. If you're in that region of practical equivalence and the test is still inconclusive, it will give you that outcome. So these could be ways to avoid some of these false positives from early stopping. So my concluding thoughts on this are on Bayesian versus frequentist stats. I mean, really, I think it's the communication of win rate being easy to understand that is a main driver of choosing that. But often we would get such a large sample size in 1 week that it wouldn't matter. So you would end up with a win rate of more than 99.9% or a p-value of less than 0.001. Either way, you would have made the same conclusion. We're not talking about, in most cases, like a different product change going forward. We just find it easier to communicate. And maybe the harder questions to focus on are, have you picked your decision threshold and your success metrics ahead of time, or does your decision rule match your risk appetite? So are you being too conservative about avoiding false positives when actually you could fulfill that measurement aim with a holdout and forge ahead with some of these changes that were, as long as you felt that the risk was low enough? So I would say if there are 3 things to take away from the talk, the first is about the scientific method and really choosing things up front, like the hypothesis and the metrics, before starting the test. The second is about the explore-exploit trade-off in A/B testing. And the third is how Bayesian stats have enabled us to address that explore-exploit trade-off using win rate to quantify which treatment is better, and expected loss to quantify the risk of choosing that winner at any one time. So I should also mention that you can be part of the future of this story. We are hiring across data scientists, machine learning people, product analysts, specialized analysts in fraud or credit, any of these roles. Head to meetcleo.com/careers. It's a very exciting place to be, Cleo. And now I think it's nearly lunchtime, but we have time for some questions if you don't want to miss too much of lunch.
Sorry, there is no mic, so use your baritone voice. Scream.
Sorry. So, two small questions within one bigger question. So, when you were talking about the holdout, so it's kind of like when you split tests in machine learning stuff, but you don't do any cross-validation on that. So you just take, say, 5% of people, and you don't, like, throughout the cycle, you don't mix giving them some different kind of tests or whatever. You just hold out 5%. And for whatever, half a year, and then you run the multiple tests on others, on other 95%. I was just wondering, I mean, it does give you the control group, but that control group, especially if it's 5%, can be non-representative as well, right? So something can happen to these particular people. So you would exclude the macroeconomic situation, say, but you wouldn't exclude a particular kind of thing to those, I think, if you don't cross-validate. And the second question that comes into this is the question about the product. So you said that the ruling framework is your p-values can be quite high, or with the Bayesian is win rate quite low. So since you already developed the product, you don't really care if it's the same success rate. But I'm sure after a few months of developing the products, and if they're not showing better performance, the CEO would come and say, "Why do you spend money on developing new products?" So can you please elaborate on maybe on the relationship between the product developers, the actual and the success rate? Are they just giving you stuff to test and you're saying it worked, or is it kind of a mutual relationship between how you define what product to develop and then test and develop and kind of Bayesian approach to develop another product? Thanks.
Great. So on the first question is about, can we use cross-validation and not just a holdout? Yeah, it's an interesting one because in offline evaluation, it's very common to use cross-validation. You'd split the users a different way and then run it again. But the problem is that we can't go back in time and erase their experience. So what would be happening in practice is a bit more complicated than the slide that I showed, because the main thing we use holdouts for are measuring a squad's impact on a metric over successive tests. So we're just interested in that one squad that would be devoted to one product feature. So say it was like sign-up rate of the budget with that income classifier that I showed, right? They're trying to make the sign-up rate frictionless for the budget feature, so they would bucket the users, and then the users in the holdout would be exposed to the old budget feature as it was at the start of the quarter. But what the other squads are doing, it ignores that holdout. So those users, if another squad ended up giving 95% of the users, say, a different method of transaction enrichment, then that would apply to the budget squad's holdout as well. So sorry, I think that's a bit of a tangent, but it does show that there's more subtlety to what's going on with the holdouts than I showed. Your second question was about the sorry, can you remind me what?
Yes, so it's a question about when you said your working hypothesis, or not a hypothesis, or say a p-value or a success metrics can be pretty relaxed when you first compared it was developed for clinical trials, but in here you say it's pretty relaxed. And if both of the metrics are kind of showing, both of the features showing the same thing, you're saying, well, we can just adopt a new one and go with it. But my question would, it costs money to develop a new thing, and if it systematically shows that the new products are not showing better performance, wouldn't you have some kind of meeting between product team and the data science team where you would probably kind of try to do an iterative approach in how to develop products instead of you just getting the product and rolling the features?
Yeah. Okay. So I remember the question now. I think so. One thing to understand is that the analytics is all happening by members of the product squad. So a product squad would have like developers and product analysts, and all in it together, trying to improve these things. I think many times we actually wouldn't end up shipping something if it seemed to be roughly equivalent to what we already had. Two of Cleo's values are make a difference and iterate with data. So iterating, A/B tests obviously important to iterate with data, but also make a difference. So we take very seriously whether we thought there really was a very big uplift. If you said like, you wouldn't, you can't wave a flag and say, yay, we shipped a new thing, because it's a very data-driven culture. On your slide that you might be presenting to the whole company, you'd show, oh, it went up from 15.5 to 15.6%. You wouldn't celebrate that as a win if you haven't also made a difference. Yeah.
Question. My tone of voice is high, so that's no problem. So you showed earlier that, for instance, to validate the income detector label, to validate, you can prompt the user and say, is this correct? Yes. Is this correct? Yes. Correct? No. But it's very cumbersome to do this, especially when there are many sources of income. In case you want to infer automatically it from the behavior of the user, is it feasible, and do you have to change something to model the possibility of making mistakes in just validating the model?
This is a really interesting area because it was the topic of an entire data science festival talk, online talk by my colleague Josh Cooper. So this was about how do you collect data on whether your model is better in a way that also prioritizes the needs of the users. So I think what we found at Cleo is if by saying no, the user can immediately fix it for themselves and have a better product experience, then it's always worth putting in that check, because otherwise all of your failures are not recoverable. But if you're just going to click no and then nothing happens and it still doesn't work, then you're right. That's we've just added extra friction to the experience with no benefit that the user can immediately see. But that's a whole kind of topic in itself. But I encourage you to find the recording of Josh Cooper's Data Science Festival talk. Yes. Sure. So the question was to go back to the Bayesian versus frequentist slide. The first one. Okay. Was it this one? It was a bit further. Okay. Was it this one maybe? It was this one. Okay. Yeah. Rosie said that she'll share the slides on LinkedIn. So yeah, you'll be able to access all of the content.
I'm conscious of the time, and if we could thank Benj for his talk.